Okay, so this little video is on the Cauchy-Schwartz inequality. Cauchy-Schwartz inequality is one of the fundamental, I guess, quantities for inner product spaces. So Cauchy-Schwartz inequality is also, it's valid for any inner product space. It doesn't need to be Hilbert. And so we don't assume that it's Hilbert. Also, we're going to let, the norm here is going to be the norm that's induced by the inner product. So we haven't specified what the inner product is or what the space is. We just have a norm that's induced by the inner product, and that's all we need to be able to prove this theorem. Okay, so this theorem says that for every x and y in our vector space, we have that the absolute value of the inner product of x, y is less than or equal to the norm of x, norm of y. And if we're in a complex world, then of course the absolute value of x is going to be the square root of the real part of x squared plus the imaginary part of x squared. So that's the what we mean by absolute value. Or if it's real, then it's the standard absolute value. Okay, so the Cauchy-Schwartz inequality holds, and this the inequality here is equal. There's an equal sign if and only if y is equal to alpha x. So in other words, if we have our vector x, if alpha is some scalar, if it's aligned, or if y is aligned with x, then we will have equality. Otherwise, there will be inequality. Okay, so how do we go about proving the Cauchy-Schwartz inequality? And again, the proof, will only depend really on this, the fact that the norm is an induced inner product and properties of the inner product. Okay, so we're going to play this little trick here. We're going to, the first thing we're going to do, clearly notice that if either x or y is 0, then this inequality holds, right? Because the inner product of x with 0 or 0 with y is going to be 0. And then on the right-hand side, the norm of 0 is 0. So we'll get 0 equal to 0. So let's assume that both x is not 0 and y are not 0. So we'll be able to, for example, divide by the norm of x or y. Because properties of a norm, the norm of x is equal to 0 if and only if x is equal to 0. Okay, so we're going to play this little trick here. We're going to look at the absolute value of x minus alpha y. And alpha will be something we choose later. Notice there's no alpha up here in the Cauchy-Schwartz inequality. And we'll get rid of alpha a little bit later. Okay, so this is an induced norm. So the norm of x minus alpha y squared is going to be the inner product of x minus alpha y with itself. And now we start multiplying this out. We have x inner product with x gives us this. We have minus alpha y with x. We get here. We get, x with alpha y is here. And then plus alpha y inner product with alpha y. So we get this term. And now we notice that the alpha on this term and this term, are in the second place. So we're going to play our little trick of taking the complex conjugate twice for these two terms. And then that allows us to swap the order here. So this is an alpha y. We'll swap the order. And then, of course, we swap the order here to get rid of one of the complex conjugates. And then we can pull out alpha. And when we pull out the alpha, we'll get an alpha conjugate here. And then alpha conjugate like that. And so then we switch the order back, to get y with itself. And then we can rewrite this this quantity with noting that x with itself is just the norm of x squared, and y with itself is the norm of y squared. Okay, so we have this statement, and now we'll notice that this is basically a a squared term in alpha. So we got to go back to completing the squares. And completing the squares is a little bit tricky with complex numbers, but just remember the idea with real numbers. If we have ax squared plus by plus bx plus c, the way we complete the square is we first pull the a term out of these first two. So we pull the a term out, we have a x squared plus b over ax, and then we think of this as, anytime we're going to have, say, an x plus alpha squared, this is going to be x squared plus 2 alpha x plus alpha squared, and so we think of this term as that guy, and so we complete the square and write, a, and then we'll have an x plus, so we have to take this term and divide by 2, x plus b over 2a squared, but of course we've got the alpha squared, so there's going to be b over 2a squared gives us a b squared over 4a squared. That should be a squared term there, plus the c comes down. Okay, so this is called completion of squares, and if we want to do that with a complex number, we basically, this is the expression that we had before, but we're going to pull y squared out here. It's kind of like pulling the a out of the previous term. So we're pulling the y squared out, and now what's left is going to be the alpha conjugate, and then we have our, it's just, this is the alpha, this is alpha complex conjugate, and so we're just going to pull all of these terms out here, but we have to divide by the norm of y to get this expression. Okay, now we're going to do a completion of the square. So in other words, we want to find some way to write this guy as a, alpha minus a term times alpha complex conjugate minus the complex conjugate of that term. So if we look at this guy and multiply it out, we have alpha complex conjugate. We have alpha times the complex conjugate of inner product of xy here, and then we have alpha complex conjugate times xy, and then what's left is going to be it's going to be inner product of xy with its complex conjugate, which is the absolute value of the inner product squared. And then on the bottom, we're going to have a y to the fourth, and we multiply by y squared, and so we'll have a y squared like that. And then, of course, the x squared comes down. Okay, so now what we're going to do is get rid of our alpha. We're going to pick alpha to make this term 0. Okay, so if we pick alpha star to be inner product of xy over y squared, then we know that the norm of x minus alpha star y squared, this term all goes to 0, and all we're left with is x squared minus absolute value of xy. And we know that this term, for any alpha, the norm is always going to be greater than or equal to 0. So this term here is greater than or equal to 0. And the y squared, we can move, this guy to the other side and multiply by y squared to get this term. And then if we square root, we get the Cauchy-Schwartz inequality. So that is the proof of the Cauchy-Schwartz inequality, and it holds for every x and y in S. Oops.